Thank you. So what I'm going to talk about is joint work with the 20% model. I will start by calling the definition of simple homotopy equivalence. So first, if we have a finite CW complex X, then we define an elementary expansion, which is the operation of adding two cancelling cells to X. It can be described by taking an n cell Vn, dividing its boundary into two parts, two n-1 cells, and gluing one of them to X, ring map. And the result of this is that in the cell decomposition, the other n-1 cell and the n cell gets n of X. And this operation is the equivalence. It has an inverse, which is deformation retraction from the union to X, which will go an elementary collapse. And if we have two finite complexes and a homotopy equivalence between them, then we call this homotopy equivalence simple if it is homotopic to a composition of some elementary extensions of complexes. And we call the two cell complexes simple homotopy equivalence if a simple homotopy equivalence between them exists. And from the definition, we can immediately see that every pair of simple homotopy equivalent complexes is homotopy equivalent. So this is a priori stronger equivalence relation. The question that we are investigating is it strictly stronger relation. And in general, yes, there are examples of complexes that are homotopy equivalent but not simple homotopy equivalent. But this actually depends on the fundamental group of this complexes. For example, in the simply connected case, homotopy equivalence is the same. And I'm interested in the classification of manifolds. So I will consider not the arbitrary CW complexes, but a pair of manifolds and ask the question whether in this setting is it true that if manifolds homotopy equivalent, are they always simple? Okay. And in low dimensions, we know the classification of manifolds. So in dimensions 1 and 2, if manifolds are homotopy equivalent, then they are automatically homeomorphic. And due to the result of Chapman, homeomorphism is always a simple homotopy equivalence. So in these dimensions, homotopy equivalence and simple homotopy equivalence are the same. In odd dimensions, at least 3, there are examples of length spaces that are known to be homotopy equivalent, but not simple homotopy equivalent, showing that in these dimensions, the equivalence relations different and practical results from but however, somewhat surprisingly, the case of even dimensions, at least 4, is still open or has been open until recently. And no examples of homotopy equivalent but not simple homotopy equivalent even dimensional manifolds were known in the literature. And our result is the construction the first such examples. Okay, so the reason why we are interested in a simple homotopy equivalence of manifolds is basically the h-cobordant theorem. And just to recall the definition, if we have cobordism between two manifolds with the property that the inclusions of the two ends are homotopy equivalences, then we call this an h-cobordism. And if the inclusions are simple homotopy equivalences, then we call this an s-cobordism. And the h-cobordism theorem, at least the first version of it states that in dimensions at least 5, an s-cobordism is always a cylinder, which implies that the manifolds at the end have geometry. So this shows that the role of the equivalence relation of simple homotopy equivalence in the diffeomorphism classification of manifolds, which is kind of our main motivation for studying it. And just as a remark, that this is actually also true in the four-dimensional case, the topological category, at least as long as the dimensions are good in the sense of grid. And the main tool for studying the relation of simple homotopy equivalence is Whitehead torsion. So if we have the homotopy equivalence between finite cylinder complexes, then we can define the Whitehead group associated to the fundamental group and an invariant, which is called the Whitehead torsion, associated to the homotopy equivalence. And this is a complete obstruction to the homotopy equivalence being simple. I will just quickly recall the definition of these objects, the Whitehead group and the Whitehead torsion. So if we start with the group G, then to define the Whitehead group first, we take its integral group ring. Over this integral group ring, we take the invertible matrices size n by n, and these of course come with an inclusion into the group of matrices of size +1 by n +1, and we can take the limit, that is GL of the group ring, and the Whitehead group is defined as the portion GL of the group ring by portion divided by elementary matrices and the elements of the group up to some. So this definition is very similar to the definition of K1 of the group ring, which would be just GL of the group ring modulo the elementary matrices. So the Whitehead group is a portion of K. Okay. And this construction can be shown to define a functor which is covariant from groups to other groups. Okay. And I will also tell you that the definition of a Whitehead torsion, at least in a simple spectral case. So suppose that we have finite CW complexes with the same fundamental group and the homotopy equivalence between them. Then we can take the several chain complexes with the G coefficients, and in these chain complexes, the cell decomposition of the CW complexes determines the basis, at least up to multiplication by group elements. And the homotopy equivalence F induces a chain homotopy equivalence. And we can consider a simple special case when this chain homotopy equivalence has the property that in each dimension it is invertible. So this means that in each dimension I, it is given by an invertible matrix Fi. Of course, this is not general, but the reason to consider this special case is because in this case, at least I can tell you the definition of the Whitehead torsion, which will be more complicated otherwise. Namely, in this special case, we have these invertible matrices in each dimension I, and we can just take their alternating sum, similarly to the Euler characteristic. And by definition, this will represent the Whitehead group and this element. And the Whitehead group has been computed in a number of cases. For example, for the trivial group, the Whitehead group is also trivial. This is the reason why every homotopy equivalence between simple Banach spaces is a simple homotopy equivalence. Similarly, the Whitehead group of free and free arbel is always trivial. But there are also examples of non-trivial Whitehead groups. For example, for finite cyclic groups, the Whitehead group is finitely generated free abelian. and its rank can be computed from the order. And in particular, the fact that the Whitehead group of cyclic groups is non-zero is what makes it possible for length spaces to be homotopic, simple homotopic equivalent, as these have finite cyclic integers. So I will also recall the definition of these because we will also use it later. So to define a length space, we need to specify a dimension 2k minus 1. So that's an odd dimension at least 3. A positive integer m, and k positive integers that are each co-prime to n. And we can view the 2k minus 1 dimensional sphere as the unit sphere in the k-dimensional complex space and define an action, the cyclic group set n, on this sphere where the action is determined by these extra numbers you want to qk that we choose. And the length space associated to this data is the quotient of this action. This action is free, so the quotient is a manifold with the fundamental rule. Okay. And the result that there are three-dimensional length spaces with fundamental group Z7 that are homotopy equivalent, but simple homotopy equivalent. So if we can see these length spaces as odd-dimensional examples of homotopy equivalent, but not simple homotopy equivalent manifolds, then when we try to construct even-dimensional manifolds, then our first idea may be to consider two length spaces and take their product with S1 and see if maybe they have the property that they are homotopy equivalent, but not simple homotopy equivalent. But it turns out that this is not the case. If the length spaces are homotopy equivalent, then after multiplying them by S1, the results will be simple homotopy equivalent. In fact, this is true in an even more general setting. If we have two pairs of odd-dimensional manifolds, such as an m is homotopy equivalent to m prime, m is homotopy equivalent to m prime, then the products then will be always simple homotopy equivalent to m prime times m prime, even if the original manifolds are only homotopy equivalent. And the reason for this is because we can take the homotopy equivalence between m and m prime, and then m prime, and take that product. And there is a formula for computing the Whitehead product. This formula computes the Whitehead product in terms of the Whitehead versions of the original maps and the Euler characteristics of the manifolds. And now we have odd-dimensional manifolds, so the Euler characteristics are 0. So the Whitehead product of the product map will be automatically 0. In particular, the product map will necessarily be simple homotopy equivalence. So because of this, we construct examples of even-dimensional manifolds that are not simple homotopy equivalent. We will need to find a different strategy. Okay, so the idea is that we will first just fix one of the manifolds that we want to be in an example that we will choose in some special ways. And as a first step, we will need to construct homotopy equivalence from some other manifold n to a total manifold n, which is not simple. But this is not enough because it may happen that if we have such a homotopy equivalence from n to n, that there may be another different homotopy equivalence, let's say limited by g, from also within the same manifolds that is a simple. So at the second step, we will need to exclude this possibility. And To do this, we will need to investigate the homotopy automorphisms. Basically, the idea that we are using here is that if we have chosen homotopy equivalence F and the simple homotopy equivalence G, then we can compose one with the inverse of the other, and we get a homotopy automorphism M with the property that is the Whitehead torsion is the same as the Whitehead torsion of the homotopy equivalence. Yeah, that we started with. Okay, and this gives us a way to exclude the possibility that the simple homotopy equivalence exists, because we need to exclude the possibility that the homotopy automorphism of M exists, which has the same Whitehead torsion. So we will aim to find manifolds M that have few homotopy automorphisms, or at least with homotopy automorphisms have the restricted Whitehead torsions. Okay, and just going back to the first step, how do we construct homotopy equivalence which is not simple to begin with? For this, we will use the strong version of the algebraic theorem, which states that in dimension matrix 5, if we fix a manifold M and the fundamental element G, then for every element X in the Whitehead group, there exists an h-cobordism M, such that the inclusion from M to the cobordism has Whitehead X. And if we have an h-cobordism, that means that the inclusions of the two ends homotopy equivalences. So again, composing by one inclusion by the inverse of the other, we get a homotopy equivalence between the two ends. And there's a formula for computing the Whitehead version of this composition in terms of the Whitehead version of the inclusion, which was X, and this composition will have Whitehead version plus or minus X bar minus X, where X bar denotes the standard evolution. And this means that as long as we can find an element X in the Whitehead group with the property that plus or minus X bar minus X is non-trivial, we can use the h-cobordism theorem to construct an h-cobordism and get a homotopy equivalence between the two ends, the h-cobordism which has Whitehead version X bar minus X, so it's not a single. Okay. So to be able to do this, we will of course need to understand the Whitehead group of the fundamental group and the involution. Okay. And the examples that we will consider will be still the same type of manifolds that I mentioned earlier. We take a length space multiplied by S1, in which has fundamental group Z plus Zn. And by investigating the Whitehead group, the involution of the Whitehead group, we find that aside from a finite number of exceptions, this Whitehead group always contains non-zero elements of the required form. So this allows us that to complete the first step of our strategy and find non-simple equivalences, some manifold. And the second step that we need to take care of is looking at the homotopy equivalences of the chosen manifold. And with S1 times L, we are in a very nice situation because we can show that every homotopy automorphism of this manifold is simple.
By homotopy automorphism, you need homotopy self-equivalence?
Yeah. So the reason we can do this is because the length space L has a very simple cell structure, just one side in each dimension, analogously to real projective spaces. So S1 times L still will have at least two cells in each dimension. So yeah, after some simplifications, we can look at the definition of the binomial. Look at the chain homotopy equivalences in these relatively simple chain complexes and show that they all have vanishing torsion. Okay. And by combining these two results, then we get that, again, if M is not one of those finitely exceptional values, then there exists a 2k-dimensional manifold that is homotopy equivalent but not simple homotopy equivalent to F times the space. Okay. So we cannot precisely tell what this manifold is, but of course, from our earlier considerations of the observation, we can tell at least that this M cannot be another manifold of the form S1 times the space. Okay. So this is the first main result of finding examples of even-dimensional manifolds that have homotopy equivalent but not simple homotopy equivalent. And of course, as we saw, this largely depends on the fundamental. And all of these examples that we found so far have fundamental root Z times M. So that raises a follow-up question. Is this some special property of the group Z times M, or there are examples with other fundamental groups? Or more generally, for which fundamental groups can we show the existence of such examples? Okay. So first, I want to start with showing the necessary for the fundamental group. And first, I can modify fashion because so far our examples were really not just homotopy equivalent but h-cobordant because we constructed them using the h-cobordant. So what we can show is that under some condition, h-cobordism always will imply simple homotopy equivalence. More precisely, if we look at the Whitehead group and we look at the elements of the form plus or minus x bar minus x, this is a subgroup, and if this subgroup is trivial, then any pair of h-cobordant will necessarily simple homotopy equivalent. And the reason for this is this formula that I mentioned a few slides ago, that if we have an h-cobordism between two manifolds, then by composing the homotopy equivalences, we get a homotopy equivalence between the two ends, which has Whitehead constant of the form x bar minus x, where x is the Whitehead constant. So if all elements in the Whitehead of this form are 0, that means that this homotopy equivalence between the ends will have vanishing Whitehead constant, so it is simple. So these manifolds cannot be constant. Okay, so this is how we get a necessary condition from the fundamental group, and our result in general is that this condition is also sufficient. And the basis for this is a construction, a family of manifolds that behave similar to S1 times the space, in the sense that all of them are simple. And the way we can do this is we take a manifold of some dimension k, and we take an orientable sphere bound over it. The only restriction here is that the dimension of the sphere has to be larger than k, it has to be. And the total space of such a sphere bundle always have all homotopy. And of course, the fundamental, the total space is the same as the fundamental group, the manifold K that we start with. And if the dimension was at least 4, then we know that every finite dimension can be realized as a fundamental group. Okay, and the consequence of this is that when the dimension is large enough, and then we can start with an arbitrary finite representative group, and we get that the condition on the right-hand group that the subgroup of elements of the form x bar minus x has to be non-zero is both necessary and sufficient for the existence. For example, of a pair of manifolds that are homotopy equivalent but not simple homotopy equivalent. And the fact that this is sufficient comes from the construction of the sphere bundles and the application of the h-cobordant surface. Before, for the sphere bundles, we can find another manifold with a non-simple homotopy equivalence into the sphere bundle. And because every homotopy is simple, and just as in the previous case, we will get that each pair of manifolds using all these simple. So the upshot is that we get a precise, if and only description for the groups that are the existence of manifolds that are h-cobordant. And I will start at this point. Thank you.
Why is n equals to 10 not included here? Why is this fraction not number?
Yes, so if you look at the number of the dimension of the sphere bundle that can be obtained, so we have to take the dimension of k to be at least 4, and if it is 4, then the dimension of the sphere can be 5 or some larger odd number. So this means that the dimension can be 9 or any larger odd number. But if k is 5, then j has to be 7. So it can be 12 and any larger. Yes.
In your example with the lens space-time of the circle that you know that there exists a manifold which is homotopic equivalent but not simply homotopic equivalent. So,
Yeah.
So the way you construct this cobordant, you multiply the lens space-time of the circle by interval in attached cells. Do you know something about the cells you need to attach, or you just know completely nothing?
Not much. So the way you would do this is you started picking an element x in the y-hat group, and you can represent it by an invertible matrix, some finite size, say k by k, and then you will have to. You can start by attaching k the trivial handles of a given dimension, and then k other handles of dimension one above.
But you don't know how.
Sorry?
You don't know how.
Well, the matrix would be fine. The attraction. And if we could get a bound on the size of matrices that represent the elements of the y-hat group, then we could get a bound on the number of handles that
Okay, so in principle, we can figure out.
In principle, we could.
Thank you.
I'm just curious about the techniques you use. Should we always about the y-hat group and the solution things and properties? So is it kind of algebraic that you're doing?
And yes, this is very much algebraic. So we have to study here the y-hat group of z plus m, which is very close to k1 of z plus m. And there is a formula expressing that k1 group as k1 of zm plus k0 of zm plus some extra terms. And it turns out that that formula also is also compatible with the evolution. So we can study it term by term and look at the equation of each term. And well, Tony Nicholson is the expert on this, but these calculations involve a lot of representation theories, algebraic.
Is it still open that the right-hand torsion of the torsion free group is trivial?
I think that's good.
Can you return to your last slide?
Yes.
So, wondering when these sphere bundles exist. Can you say anything about that? Like when I have such a thing?
Well, you can always just take a trivial sphere bundle.
Sure. But like, so do I get anything more interesting than a trivial sphere bundle? Like, we're trying to find things about n.
Yes. Well, you could get actually more interesting manifolds. So a sphere bundle is a special case of a double. You can take a disk bundle over K, and you can just double it to take two copies of it and glue them around the boundary with the identity map, and then you get this. But under some restriction on the glue map, you can obtain other doubles, other 50 doubles that are not sphere bundles,
Yeah.
but still have the same property.
So if there are any more questions, let's move this again.